In this video, we will be looking at section 4.3, which covers logarithmic functions. So first we're going to start by talking about what a logarithm is. The logarithm base b function, written log base b of x, so that's what that subscript is, it's the base. So we read this as log base b of x, is the inverse of the exponential function base b to the x. So what it is it's kind of the reverse process. So because these two functions are inverses, if we compose them together, then they undo each other. So log base b of b to the x is equal to x, and b raised to the power of log base b of x is also equal to x. If you know anything about logarithms, this is the thing I need you to know. The statement b to the a power is equal to c is equivalent to the statement log base b of c is equal to a. When it comes to logarithms, this is going to be key as it's going to help you solve so many things. One way that my students try to remember this is by using what they call the snail method. And what it does is you create kind of this snail spiral, and that helps you remember the order of things. Now this little snail spiral only works if your exponential is on the left or if your logarithm is on the left, depending on which equation you're looking at. So you'll notice with the way I did my snail, I went b, c, a. If you go down the line for writing my logarithm equation, log base b of c equals a. If I do the snail on my logarithm, then the order that I hit the variables in is b, a, c, b to the a power equals c. So that kind of order might help you remember it. If that doesn't work for you, forget I said it. I just wanted to give you one method to help you remember. We're going to practice going between logarithmic and exponential form. So starting with some logarithm equations, we are going to switch them into exponential form. So first up we have log base 2 of 8 equals 3. If I use the snail, I will get 2 to the third power equals 8. And that's how I write it in exponential form. Log base p of m equals w would be p to the w power equals m. Now we're going to look at some exponential equations and see if we can write them in logarithmic form. First up we have 4 to the third power equals 64. If I use the snail, we'll get 4 64 3. So I would write that as log base 4 of 64 is equal to 3. Next up we're looking at b to the r power is equal to g. So that would be log base b of g is equal to r. Being able to go back and forth between these two forms is going to be essential moving forward, so make sure you're able to switch between these two. There are two types of logarithms that our calculators can definitely do. Some calculators can do more than just these two, but these are the two that are guaranteed to be on any scientific or graphing calculator. They are the common log and the natural log. The common logarithm is the logarithm with base 10 and is typically written log of x. So if you ever just see something like the log of 2, where you don't see a base, it is implied that there is a base of 10. That's just one of those things that we know. If we don't see one, it's a base 10. The natural log is the logarithm with base e and is typically written ln of x. So if you see, say, ln of 2, we would say this out loud as the natural log of 2. That means the same thing as log base e of 2. Now this common log and natural log do have buttons on your calculator. So for example, the log of 2, here's your log button. And if we want the log of 2, I'll press log and then 2. If I close my parentheses, I get that the log of 2 is about 0.3010. The natural log of 2, the ln button is under log, and the natural log of 2 is about 6931. So those two buttons should be on your calculator somewhere. We're going to solve some logarithmic equations. And like I said before, being able to switch between logarithmic and exponential forms is going to be essential. And here is one of the examples of where that can come into play. So we are solving for x. In the first equation, we're looking at log base 5 of x is equal to -1. So if I put it in exponential form, I'll have 5 to the -1 power is equal to x. I've solved for x. I found what it is. But just so we can write it in a nicer form, 5 to the -1 is equal to 1 over 5 to the +1, which is just 1/5. So what we're really saying here is x is equal to 1/5. If the log of x is equal to 5, we don't see a base. When we don't see a base, then that base is 10. So if I write this out in exponential form, we will have 10 to the 5th power is equal to x. Yet again, I've solved for x, but it's nicer if we can have it in like a form that we understand. So 10 to the 5th power is equal to 100,000, so we get x is equal to 100,000. Finally, we have the natural log of x is equal to -2. Natural log has a base of e, so if I put my e down there, then we will have e to the -2 is equal to x. Kind of like we did with the negative exponent before, I could rewrite e to the -2 as 1 over e squared. That's not particularly pretty either. You should have an e button on your calculator. If you have one of these TI graphing calculators, you actually have 2. So you can get to e by going second divide, and that'll give you just an e. Or you can go second ln, and that'll give you e raised to a power. We're looking at e to the -2, and we're getting about 0.1353. I'm not really sure whether a decimal or a fraction is better in this case. Use your best judgment. So now that we've solved some logarithmic equations, we're going to see if we can simplify some logarithmic expressions. So first up, we're looking at log base 2 of 8. Well, my calculator doesn't have a log base 2 button, so I'm going to have to figure out another way for how to express this in a simpler way. So right now, I'm just going to say that log base 2 of 8 is equal to x. If I now write that as an exponential equation, I will have 2 to the x power is equal to 8. So I can ask myself, 2 raised to what power is 8? Well, that's 3. So we get x equals 3. That means log base 2 of 8 is equal to 3. Next up, we're looking at log base 6 of 1/36. Since I don't know what it is yet, I'll call it x. So that'll be 6 to the x power is equal to 1 over 36. And this one might not come quite so easily to you. What I do know is 1/36 I can rewrite as 1 over 6 squared, because 6 squared is 36. But 1 over 6 squared is the same as 6 to the -2 power. So if I go back to this equation that I have, that would be 6 to the x power is equal to 1/36. But we said that 1/36 is 6 to the -2. So if 6 to the x is equal to 6 to the -2, then we get x equals -2. So log base 6 of 1/36 is equal to -2. These last two, we could do the whole set equal to x thing, but we have these buttons on our calculator. So let's type in the log of 0.0001 That's equal to -4. And then the natural log of e cubed, so e to the 3rd power, is just 3. And I kind of want to look at that one a little bit closer just because it seems weird that the 3 in the exponent ends up being the answer. And the reason for that is natural log is just log base e. So we're asking ourselves, log base e of e cubed is equal to what? So if I put that into exponential form, e to the x is equal to e to the 3. So x equals 3. So that's where that's coming from. Now, like I said, my calculator doesn't have a log base 2 or a log base 6 button. Some people's do. Ask me in class and I'll help you find it if your calculator is one of the special ones. But if your calculator doesn't have the ability to do bases other than 10 or e, then we're going to need the change of base formula. The change of base formula says log base b of a is equal to log base c of a over log base c of b. So if we have something like log base 12 of 93, something really weird, then I can change this log to be any base I want. My calculator does common log and natural log, so I can choose either one. Let's do common log first. That'll be equal to log of a, so that'd be 93, divided by the log of the base, which is 12. But like I said, it can be any logarithm as long as they're the same. So I could also use the natural log. So I could type this in as the natural log of 93 over the natural log of 12. Either way, you're going to get to the right place. So let's practice using our calculators a little bit. We're going to evaluate the following expressions. First up, we have the log of 4. Log 4 equals. Generally, it's pretty acceptable to go out to 4 decimal places, so that's what I'm going to do in this case. I'm looking at the log of 4 is about equal to 0.6021. Next up, we have the natural log of 14. So the natural log of 14 equals, I'm getting about 2.6391. Next up, we're looking at log base 5 of 72. I'm going to have to use the change of base formula here. It doesn't matter if I use common log or natural log. I'll use natural log because it's a whole 1 letter shorter to write. So we'll have natural log of 72 over the natural log of 5. Be sure when you're typing these in, you have to close the parentheses on your logarithm in the numerator. If you don't, you will get the wrong answer. So if we do the natural log of 72 divided by the natural log of 5, I'm getting about 2.6572. For the log base 2 of 1/8, I can type that in as the natural log of 1/8 divided by the natural log of 2. The natural log of 1/8 divided by the natural log of 2 is equal to -3. And hopefully that makes sense because 2 to the -3 power is equal to 1/8. Finally, we're looking at log base 0.3 of 15. So that will be the natural log of 15 divided by the natural log of 0.3. And the natural log of 15 divided by the natural log of 0.3 is about -2.2493. So make sure you get in some practice using your calculator. That way you will be comfortable using it in the future. Up next, we have Amanda's favorite log rule. I cannot tell you why this is my favorite log rule. It just is. Ever since I learned about logarithms the first time around, I thought this was the coolest thing. Bad news is if you go on Google and type in Amanda's favorite log rule, this probably won't come up. So it's also known as the exponent property, at least when it comes to logarithms. What it says is log base b of a raised to the r power is equal to r times log base b of a. So if you have an exponent inside your parentheses, you can bring it out front as a factor and multiply it. So for example, if you're looking at log base 2 of x to the 5th power, you can bring that 5 out front and write it as 5 log base 2 of x. This is going to help us when we're solving exponential equations. So the steps for solving exponential equations, first we want to isolate the exponential expression if possible. So wherever we have a variable in the exponent, try to get that piece all by itself. Then you're going to take the logarithm of both sides. You can then utilize the exponent property for logarithms, aka Amanda's favorite log rule, to pull the variable out of the exponent, and then we're going to use algebra to solve for the variable. So here I have 4 examples of some exponential equations we're going to solve. I'm going to pull out a separate sheet of paper so that I know I have plenty of room, because I have a feeling it's going to get close sometimes. So first up we have 3 to the x power is equal to 23. So the first step of solving exponential equations is to get the exponential by itself if possible. 3 to the x, it's by itself. We're looking good. Now we're going to take the logarithm of both sides. It doesn't matter if you take the common log or the natural log. Whatever you do, it's totally fine. If we do common log, then we'll have the log of 3 to the x is equal to the log of 23. Amanda's favorite log rule says that exponent can now move out front, and we will have x times the log of 3 is equal to the log of 23. I'm trying to solve for x, and right now x is multiplied by the log of 3, so to get the x by itself, I'm going to divide by the log of 3. And I have to do it on both sides so that it stays equivalent, and we get x is equal to the log of 23 over the log of 3. And that's our answer. That is what we call an exact answer because we didn't do any rounding. That is precisely what our answer is. If you wanted to type it in the calculator and get a decimal approximation, you can, but this one, no rounding, so we are spot on. Next up, we are looking at 4 raised to the 2x minus 3 power is equal to 44. First step is to get the exponential by itself, which it is. It's just 4 raised to a power on the one side. So now we take the logarithm of both sides. This time I'll use natural log just to show that we can do it either way. So we'll have the natural log of 4 raised to the 2x minus 3 power is equal to the natural log of 44. I'm going to use Amanda's favorite log rule to pull the 2x minus 3 out front. Keep in mind that that 2x minus 3 is a group, so I'm going to keep it in parentheses. That's multiplied by the natural log of 4 and is equal to the natural log of 44. Now I could distribute my natural log of 4 to the 2x and to the negative 3, but instead I'm going to notice that the natural log of 4 is multiplied by this thing. So instead I'm going to divide both sides by the natural log of 4. What that leaves me with is 2x minus 3 is equal to the natural log of 44 over the natural log of 4. Remember, I'm still solving for x, so I'm going to add 3 to both sides, so that 2x is equal to the natural log of 44 divided by the natural log of 4 plus 3. And then I'm solving for x, so I need to divide by 2. X is equal to the natural log of 44 over the natural log of 4 plus 3, all divided by 2. And that doesn't even look right. I'm going to put my x equals all the way up front. Keep in mind that what we're doing here is we are solving equations. The good news about solving equations is you can always check your answer. I'm going to check my answer on this one because it is so complicated, but the good news is our calculator has ways of helping us get there. So x is equal to the natural log of 44 divided by the natural log of 4. To that, I need to add 3, and then I need to divide by 2. What I'm going to do is I am going to store this, so STO arrow, as x. So now if I go back to the original equation and I type in 4 raised to the power of 2x minus 3, we're hoping to get the answer of 44. Yay! So when we're solving equations, we can check them. So that's kind of cool. Let's move on to this next one. We have 2 times 1.08 raised to the 4t power is equal to 7. First step is to get the exponential by itself. Right now, our 1.08 raised to the 4t power is multiplied by 2. So I'm going to divide both sides of this equation by 2 so that the exponential is by itself. Then we'll have 1.08 raised to the 4t is equal to 7/2 because I divided both sides by 2. I'm going to take the log of both sides. We'll use common log this time. So the log of 1.08 raised to the 4t is equal to the log of 7/2. Amanda's favorite log rule says I can now take that 4t out front. So 4t times the log of 1.08 is equal to the log of 7/2. I'm trying to get the t by itself. Right now t is multiplied by both 4 and the log of 1.08. So I'm going to divide both sides by both the 4 and the log of 1.08. We get t is equal to the log of 7/2 divided by 4 log of 1.08. That's our answer. Last one, we have 10e to the negative 0.03t equals 4. Trying to solve for t here. First step is to get the exponential by itself if we can. So I'm going to divide both sides by 10. That'll give us e raised to the negative 0.03t power is equal to 4/10. But 4/10 reduces to 2/5. So we have e to the negative 0.03t equals 2/5. I'm going to take the log of both sides, but because I see an e, I'm just going to use natural log. It just seems, wait for it, natural to do so because there's an e in the problem. I am hilarious. You're welcome. So I'm going to take the natural log of both sides. So the natural log of e raised to the negative 0.03t is equal to the natural log of 2/5. I can bring my exponent, negative 0.03t, out front. So negative 0.03t times the natural log of e is equal to the natural log of 2/5. But, check this out. The natural log of e is equal to 1. So what I have is negative 0.03t times 1, which doesn't change anything, is equal to the natural log of 2/5. So to solve for t, I divide both sides by the negative 0.03. So t is equal to the natural log of 2/5 divided by negative 0.03. And we have our answer for t.